Good afternoon. I thank the organizers for giving me this opportunity to present my work. So today I will be talking about polymer translocation through extended pores. So it has not come, yeah. So this work is done by my PhD student Andri Sharma. So all simulations were done by Andri Sharma. So she is now a postdoc in South Korea, and my this work Abhishek is a collaborator in this work. This work got recently published in this this reference. So if you want to know more about this, you can learn from this one. So the main thing we are talking about here in this work is the scaling of a translocation time. So polymer translocation is a very important problem. So it has a biological reference. Say for example, your DNA, RNA transport through nuclear pores can happen, and protein translocations. So these are some of the cartoons of nuclear pores. So these are three different biological pores. All are extended pores. We have a cylindrical pores. These two are cylindrical pores, and this is a conical pore. Also, polymer translocation has technological applications. So, for example, this is a commercially available device called MinION pore from MinION device from Oxford Nanotechnology. So it's a very small device which can be used as a USB, can be inserted from the USB port, and can be used for doing DNA sequencing. So polymer translocation is a non-equilibrium process. So because the translocation time is often much shorter than the polymer relaxation time. And it has been successfully explained by tension propagation theory, which was proposed by Sakaue and then modified for finite chains by various researchers. And so in this theory, the dynamics is driven by a tension front which moves along the chain. So I will not talk about many things here, but the most important quantity in polymer translocation is to see what is the average translocation time for the polymer to translocate through a pore. And for by numerical simulations and some experiments, it was found out that for a self-avoiding flexible polymer, the average translocation time scales with the chain length by this particular scaling, where the size exponent is 3/4 in 2D and 0.59 in 3D. So these all scalings, whatever these scalings were done for unit length pore, a membrane, a polymer translocation through a membrane. But we have seen that the real world pores are extended pores, and so even inside that extended pores, there are pore polymer interactions which are different. So we try to ask what happens, how this scaling modifies when we have, say, extended pores and spatial patterning. So how do pore length and patterning influence the physics of single molecule transport? So we again did Langevin dynamic simulations in 2D. Our model is a bead spring chain. So this is basically the equation of motion in this particular part, and then we use LAM software, averaged over around 2,000 successful events per data point, and so these are the geometries, different geometries and different patterns we try to study. So this is a schematic diagram of our study. So we have a extended pore. A polymer translocates through the cis end and goes towards the trans side. So the width at the cis end is small enough so that only a single file translocation is possible. So there is an external force which acts inside the pore. So all monomers which are inside the pore feels this external force. and we can vary this angle alpha to make it a cylindrical or a conical pore. So we also took 3 different type of pores. So we have a pore A is a uniform attractive pore. So the pore is fully attractive. All beads are attractive in this case. We can have an attractive entrance. So another type of patterning we have is we have an attractive entrance. Then we have also attractive exit, but in between there is a repulsive middle section. And the third type of pore is we have an attractive entrance and a repulsive exit. So then the way we vary our pore is, so we study these 3 different lengths of the pore. So we vary in such a way that the ratio of your attractive and repulsive segments remains conserved. And so the external force is given by this particular expression. So you can see that when alpha equals 0, it becomes a cylindrical pore, and it has a constant force F naught. But as you increase alpha, the force, the value of the force decreases as you pass along this trans site. So these are the results. So geometrical results. So here I am showing the average translocation time as a function of alpha for a uniform pore. So for this particular pore, uniform attractive pore. So for alpha equals 0, that is a cylindrical pore, we can see that when the pore length is small. So this is for F naught, the force for 1.0 units, whatever in Langevin dynamics units or something, which dimensional units we chose in this case. So for a smaller pore, the average translocation time is larger. As we increase the pore length, the translocation time decreases. So we can also explain this because now the pore is longer, so average force experienced by the polymer inside the pore is more, and so the polymer translocates much easier for the longer pores. But when this alpha increases, so basically now you are making it a conical pore, you can see that when the pore is smaller, the translocation time decreases as alpha increases, and it gets saturated somewhere. But for a longer pore, the translocation time increases and then gets saturated in this. So this for short pores, this tau decreases as alpha increases, and this is because of the entropic relief we have. This wider exit reduces the confinement hindrance. For longer pores, alpha increases as alpha increases, tau increases as alpha increases, because there is a bottleneck at the end, because the local driving at the exit side becomes smaller, significantly weaker, and therefore there is a weak this particular part. And also what we found out, this repulsive exit pore C, which is the repulsive exit, consistently favors the fastest translocation across all geometries. So to unify N and LP, a finite size scaling form, we propose this finite size scaling form, and what we found out that for all cases we have studied, there is a very good collapse obtained for these two exponent, gamma equal to this particular and phi equal to this value, where scaling function we are just having a power law scaling, from where beta can be written in terms of this particular part. Now let me show the results. So these are the scaling curves for cylindrical unpatterned pores. So this attractive uniform attractive pore. So if we plot average tau by n to power gamma as a function of LP and phi, so all curves. So these are the curves for different pore lengths and different chain lengths. So we vary both LP as well as N, and for various different force values F naught, we see that they fall on the same curve, and the scaling function is given by this power law with this particular exponent. So then we can also see for this cylindrical patterned pores, again we plot in the same fashion, and we found out that again the curves falls on a single curve, scaling curve. But only thing is that this p value changes here, becomes a different value. So for conical pores, so here we have chosen a conical pore with say alpha equal to 3 degrees, and these are results for different for a fixed force value. So we keep force fixed here. So in the previous case, we have in fact changed the force values. And here also again we see that the scaling is a very good collapse we obtained for those same exponents, gamma equal to 3 and 5. But only thing here is this one. So let me conclude. So what we found out that the longer cylindrical pore accelerates transport by hosting more driven monomers. So conical pore offers entropic relief but risk field weakening bottlenecks at large lengths. Repulsive exit patterns are optimal for rapid molecular release. And the most important result is the exponents gamma equals 3 and phi equal to 1.5 are consistent, remarkably consistent for both patterned, unpatterned pores with conical, cylindrical, all particular pores for various driving forces F0. Thank you. Yeah, so because our entrance is taken such that polymer can enter a single file translocation. But for a conical pore, if you have a wider exit, so it can make a hairpin at those particular parts. That's why there that hindrance is coming, bottleneck becomes coming.
Yeah. In a polymer translocation experiment, the width should also be important, right? I've seen data where people, these are DNA experiments, they form hairpins and all that. You don't account for all that.
So hairpins, outside hairpins are not there, but for this particular part, if you have a conical pore, so our pore, we have chosen those pores in such a way that single file translocation is for the cylindrical pores.
Sure.
But if it is a conical pore, there can happen those hairpins, and because of that, we have seen that there are this slow down of this translocation time because they get stuck inside those wider part.
Okay, so those you do not consider, is it?
No. So in this case,
it's there
we have
in the
considered,
conical
yes,
data.
yes.
Okay, thank you.
Any more questions? If not, then let's thank the speaker.